Terrestrial Planet. These are the rocky worlds of the inner solar system, built mostly from rock and metal and shaped by craters, volcanoes, mountains, and in some cases, thick atmospheres. Mercury, Venus, Earth, and Mars all belong here, and they matter because they show what a solid planet can become under very different conditions, from a scorched surface to a life-bearing world.
Gas giant. This is the classic giant planet category, dominated by hydrogen and helium and wrapped in a deep atmosphere with no simple solid surface like Earth's. Jupiter and Saturn are the main examples in our solar system, and they matter because their huge gravity helps shape entire planetary systems, influencing moons, asteroids, and the paths of smaller worlds.
Ice giant. These planets are still giant worlds, but they contain more water, ammonia, and methane-rich material in their interiors than Jupiter and Saturn do. Uranus and Neptune fit this type, and they matter because they represent a major branch of planet formation that seems common in the universe, even though our own solar system has only two. Dwarf Planet. A dwarf planet is round like a planet, but has not cleared other objects from its orbital neighborhood, which sets it apart from the 8 full planets in the solar system. Pluto, Ceres, Haumea, Makemake, and Eris are the officially recognized examples, and they matter because they reveal that the solar system does not end with the major planets, but fades into a much larger population of strange icy bodies. Super-Earth? This is an exoplanet category for worlds more massive than Earth, but still much smaller than Uranus or Neptune. Super-Earths matter because they appear to be common around other stars, and they may include rocky planets, water-rich planets, or worlds with thick atmospheres, making them one of the most important classes in the search for habitable environments. Mini-Neptune. A mini-Neptune is smaller than Neptune, but still wrapped in a thick atmosphere of hydrogen and helium, which makes it very different from a rocky planet, even when the size can seem similar at first. These worlds matter because surveys suggest they are among the most common planet types in the Milky Way, yet our solar system has none, which makes them especially useful for comparing other star systems to our own. Hot Jupiter. This is a gas giant that orbits extremely close to its star, far closer than Jupiter or Saturn orbit the Sun. Hot Jupiters matter because they were among the first exoplanets discovered in large numbers, and they forced astronomers to rethink how planets move after formation, since giant planets were once expected to stay far from their stars. Super Jupiter. A super Jupiter is an object more massive than Jupiter, reaching up to about 13 times Jupiter's mass in common classifications. These worlds matter because they sit near the blurry boundary between the largest planets and the smallest brown dwarfs, so they help astronomers study where planet formation ends and star-like formation begins. Sub-Earth. This type includes planets substantially less massive than Earth, such as Mercury-sized or smaller rocky worlds. Sub-Earths matter because they show the lower end of planet building, where a world may be too small to hold a thick atmosphere for long, but still preserve clues about early solar system formation. Ocean Planet. An ocean planet is a proposed world with a substantial fraction of its mass made of water, possibly with deep global oceans above layers of high-pressure ice. These planets matter because they expand the idea of habitability beyond Earth-like land and sea, suggesting that some alien worlds could be dominated by water from top to bottom. Lava Planet. A lava planet is a rocky world so hot that much of its surface may be molten. These planets matter because they show what happens when a terrestrial world orbits so close to its star that rock itself begins to behave like liquid, turning the planet into a window into the most extreme end of rocky planet evolution. Rogue Planet. A rogue planet is a planet that does not orbit a star and instead drifts through space on its own. It matters because it proves planets are not always tied to solar systems, and it raises the possibility that some worlds are thrown out during the violent early history of planetary formation. Circumbinary Planet. This is a planet that orbits 2 stars instead of 1, like the science fiction image of a double sunset made real. These planets matter because they show that planet formation can succeed in environments that seem unstable at first glance, widening the range of places where worlds can exist. Carbon Planet. A carbon planet is a theoretical world thought to be rich in carbon compounds rather than dominated by silicate rock like Earth. It matters because it reminds us that planets may be built from very different starting materials depending on the chemistry of the disk that formed them, leading to worlds that are familiar in shape but alien in substance.
Hycean Planet. This is a proposed type of habitable planet with a hydrogen-rich atmosphere and a water-covered surface, usually imagined as warmer than Earth, but still potentially suitable for life in some conditions. Hycean planets matter because they broaden the search for life, suggesting that a planet does not have to look much like Earth to be scientifically interesting.
Protoplanet. A protoplanet is not a finished planet, but a large planetary embryo forming inside a protoplanetary disk, growing through collisions and accumulation. It matters because every mature planet begins here. So protoplanets let us study the messy construction phase that eventually produces rocky worlds, gas giants, and everything in between.
Silicate Planet. A silicate planet is a rocky planet made mostly of silicate minerals, which includes all 4 inner planets of our solar system. This type matters because it is the baseline for how most people imagine a planet, and it helps explain why Earth, Venus, Mars, and Mercury share some broad structural features, even though their histories turned out very differently.
Chthonian Planet. This is a proposed remnant of a gas giant that has lost much of its thick atmosphere, leaving behind a stripped core. It matters because it may reveal that planets can change category over time, with intense heat and stellar radiation peeling away layers until an entirely different kind of world is left behind.